Hi, everyone. Welcome to Holistic AI's webinars on bias detections in large language models, techniques and best practice. I'm Ziken Wu, your host today. All right, it looks like most people are here, so let's get started. And thanks again for joining us today. And due to large number of participants and time constraints, please type any question you have in the webinar chart. We will answer them and post any response on event pages on the website after the event. Now, let's dive into the topic. First, let me introduce today's speakers. First, there's myself, Ziken Wu. I'm an AI researcher at Holistic AI and OECD AI, and I'm currently a PhD student in computer science at UCL, and focus on sustainable and responsible AI. The next is Xin Guan. He's an AI researcher at Holistic AI and CLAI, with BA and MPhil in mathematics and philosophy at Oxford. He's focused on AI fairness alignment. Next, we have Nick Danchuk, an AI research assistant at Holistic AI, and a third-year computer science undergrad student at Stanford. He's focusing on AI for good and biology. Next is Steve, an AI research affiliate at Holistic AI, and an economics PhD scholar at the Stone Center at UCL. He's focused on responsible AI in economics. Finally, we have Mina, an AI risk management officer at Holistic AI with MSc CS at Warwick University, and she's now focused on bias mitigation in machine learning. So before we dive into the main sections, let's quickly go over today's agendas. We'll start defining what is bias and fairness in context of AI. Then we'll move on to AI risk instance and compliance in AI systems. After that, we'll explore the source of bias in LLMs and how they arise. Then we'll look into how those bias embed in LLMs intrinsically and extrinsically. And next, we'll present some of the holistic AI bias detection research, including SAGE, which focus on generative bias detections, and JobFair, which focus on decision bias detections. We'll then follow that with information on bias mitigation courses we offer, which collaborate with the Alan Turing Institute. Finally, we'll shortly introduce our open source library to support bias detections and mitigation AI systems. So let's start by first defining what is bias. In terms of human beings and cognitive science, bias happens when actions and decisions are influenced by prior knowledge, which might be incomplete or incorrect. For example, outdated societal norms might lead to assumptions that women are less likely to become engineers. In terms of general AI systems and decision algorithms, bias show up when the models assume that certain characteristics about people based on their groups. For example, an algorithm might favor male candidates for tech job because the data show male are more frequently higher in those roles. And in terms of generative LLMs, bias occurs when there are unfair or skewed association between words or groups. For example, an LLM might generate sentences associating the word nurse more with women and doctor with men. So move to fairness. At its core, fairness in AI is about achieving equitable, just, and impartial outcome for both individual and groups. And it's generally broken into two main categories. The first is individual fairness, and the second is group fairness. Individual fairness asks the questions, am I, as an individual, being treated the same as someone with similar qualifications? And it's mainly focused on ensuring that every person receives fair treatment compared to others with similar background or credentials. The goal here is to avoid unfair bias at a personal level. And then group fairness asks the questions, is the minority group I belongs to being treated the same as the majority groups? Group fairness is about ensuring that minority groups have the same opportunities and are not disadvantaged compared to majority groups. However, the real challenge lies in balancing these two fairness concepts within AI systems, which is making sure individuals are treated fairly while also promoting equally across different groups. So let's dive deeper into the trade-off between individual fairness and group fairness, using an example of an AI system trained to screen resumes. So if the companies want to focus more on individual fairness, they will assume that everyone starts with the same opportunities. And the AI system will screen resume without consider any demographic information like gender or race, and evaluating each candidate solely based on qualifications. However, by treating everyone equally, the system might unintentionally reinforce existing inequalities. For example, historically advantaged groups, for example, male, may have stronger resume due to power opportunities, which could widen the disparities. And then, if the company wants to focus more on group fairness, it will adjust for imbalance between groups. For example, the AI system might be calibrated to ensure that a certain percentage of candidates hired are from minority groups, like women or ethnic groups. And this may involve treating equally qualified individuals differently to achieve balanced outcome, which can promote diversity, but might compromise the ideas of treating every individual equally. So what is the relationship between bias and fairness? Both concepts are very loose and have many definitions depending on the context. But in ethical AI, fairness is often the ultimate goal, but it's always required bias mitigation as a foundational step. Addressing bias, whether in data, model architectures, or evaluations, paves the way toward achieving fairness by reducing unjust impacts on specific group or individuals. So now we know what bias and fairness mean. Let's talk about why they matter. This is because bias and fairness in AI can lead to major financial losses and long-term reputational damage for companies. Let's look at some real-world example to see just how serious this impact can be. The first example is the Amazon's bias hiring tool. So the Amazon has to shut down its AI hiring tools after it was found to be biased against women. The next example is the Microsoft racist chatbot. It's called Tay AI. And this chatbot on Twitter was quickly turned into a tool for expressing racist idea within one day. As we can see, failing to ensure bias-free, fair, and ethical AI systems leads to serious consequences. These incidents don't just disappear. They are discussed for years in industry forums and webinars, like this one. So keeping the reputational damage alive. So addressing bias to achieve fairness isn't just about ethics, it's about protecting a company's financial health and public trust. So as we can see, uncontrolled AI systems are threatening the world, from bias and discriminations to privacy violations. In response, governments worldwide are putting the effort to regulate AI. And here are two examples of these regulatory efforts. The first one is the UA Act. This is the one of the most comprehensive AI regulation to date. It's categorized AI system by the risk level and imposes strict requirements on high-level risk applications, like those using biometric identifications and critical infrastructures. The goal is to create a unified standard for AI governance across the European Union, setting a global benchmark for responsible AI. And the second one is the New York City Law 144. This law focuses specifically on AI in hiring context. It's mandates bias audits for automated decision-making tools, as well as AEDT used in employment, helping to prevent discriminations in hiring practices. This is a key step in addressing real-world risk of bias, particularly in workplace setting. And these are just two examples. As this map shows, there's a global push for AI compliance. Countries across North America, Europe, Asia, and beyond are enacting their own laws to addressing challenges and risk posed by AI systems. From the US to Asia, the world is increasingly recognizing the need to control AI systems to protect society. So let's take a closer look at NYC Local Law 4, which specifically address AI systems used in employment decision-making process. Many companies use AEDT, so we call automated employment decision tools, to help with hiring. However, this system can unintentionally introduce bias into hiring practices. The law came into effect on July 5th, 2023, and it's one of the first regulations of this kind. The scope of this law is broad. It's covered any AI tools used by employers in New York City to evaluate, select, or eliminate candidates for employment. In other words, it applies to any AEDT that influence hiring decisions, affecting all employers in NYC who rely on this tool. To tackle this, the law requires that all AEDT used in NYC undergo an annual, independent, and impartial bias audit. This means that every year, these AI-driven tools must be evaluated to ensure that they aren't producing discriminatory outcome. To go a little bit deeper, a bias audit is an impartial evaluation that examines whether an AEDT is creating disparate impact, which means checking if the tool disproportionately affects certain groups, especially based on race or gender. And disparate impact occurs when an AI tool, even if designed to be neutral, ends up negatively impacting specific group more than others. For example, a hiring tool might unintentionally disadvantage women or minority groups due to the underlying bias in its data or algorithms. So now, let's walk through how disparate impact is quantitatively measured during a bias audit, specifically focus on the impact ratio calculations. For different type of ADT, we have different ways to calculate the impact ratios. For binary classification task, which the model provides yes or no, we use the selection rate. This is calculated by comparing the proportion of successful candidates across different categories, like male vs female or black vs white. And the formula is simple. The number of successful candidates from a group is divided by the total number of candidates from that group. And in terms of regression tests, where the model provides a score, we calculate the scoring rates, which is measured by the proportion of candidates from a group who score above the median and then divided by the total number of candidates in that group. After calculating the selection or scoring rates, we determine the impact ratios, which is done by dividing selection or scoring rates of one group by the rates of the group with the highest selection rate. A low impact ratio indicates a potential bias, where one group is being treated less favorably compared to the group with the highest success rate. After the calculations, we get the results. But how can we determine if the results indicate bias or disparate impact? While local law 4 does not provide a specific threshold for fairness, a commonly used guideline is the 4th-5th rules, also known as the 80% rule, established by the Equal Employment Opportunity Commissions, what we call EEOC, in the US. This rule suggests that the impact ratio should be larger than 0.8 for a selection purpose to be considered fair. If the ratio falls below 0.8, there will be a bias against that group. Now, look at the table. The Hispanic or Latino group has the highest scoring rate of 64.2% and an impact ratio of 1, making them the reference group. White candidates, however, have an impact ratio of 0.58, which is below the 0.8 threshold, indicate a potential bias. Similarly, Black or African American candidates show an impact ratio of 0.78, also falling below the threshold, indicating a potential bias. On the other hand, groups like Native Hawaiian or Pacific Islander have an impact ratio of 0.97, which is very close to the reference group, where we consider this is fair. So let's now cover other compliance requirements of NYC Local Law 4. Before using any AEDT, company must publicly disclose several key pieces of information on the website in their bias report. This transparency obligation is very important to ensure that the tools are being used fairly and responsibly. And here's what needs to be published. The first is the source and explanations of the data used by the tools. The second is the number of applicants evaluating each demographic categories. And the third one is the impact of missing demographic data and how it affects the tool's performance. The next one is distributions and audit dates of the AEDT, accompanied with the impacts of small sample size on the decision-making process, as well as the results we previously calculated, the impact ratio for different demographic groups. And the final one is an annual update summary, which must be published to ensure ongoing compliance with the law. So these transparency requirements aims to increase transparency and accountability, ensuring that any AI-driven hiring tools are thoroughly audited and the results are accessed to the public. So we've now covered the key aspect of our compliance in terms of NYC Local Law 4, but compliance is only part of the story. To effectively detect bias in AI systems, we need to understand where this bias comes from. The reality is that bias can be introduced at multiple stages during the development lifecycle of LLMs and AI systems. So when developing LLMs, we normally have 4 stages: training data collections, model pre-trainings, downstream task adaptations, and model evaluations. Each stage in the development lifecycle of our LLMs introduce unique source of biases. So during training data stages, where vast amount of test data are scripted, collected, preprocessed, tokenized to serve as a foundation of model training. However, there is also where historical and sampling bias often arise. When data reflects outdated societal norms or lack diversity, certain groups or perspectives may be underrepresented. For example, if the majority of training data comes from Western sources, the model may lack representation of non-Western perspective, leading to a biased response on topic relevant to those underrepresented groups. The next stage is pre-training stages. The model will begin learning patterns from the large data set we pre-processed before. Here, inducive bias can emerge due to the model's architectures and optimization goals, which often prioritize certain patterns or simpler, more frequent associations. These bias reflect how the model interprets data, sometimes reinforcing stereotype. For instance, the model might associate doctor with male pronouns and nurse with female pronouns. And the next one is the downstream adaptation stage, where the model providers will fine-tune the model for specific tasks or align it with human values. For example, the supervised fine-tuning SFT helps the model perform specific tasks better, while the reinforcement learning from human feedback, what we call RHF, align the model output with human preferences. But in RHF, a reward model ranks response based on the human feedback and is guiding the model behavior. And this stage can introduce human feedback bias if the feedback or reward model is biased. For example, if the human rater favors response that reflects certain cultural or ideological views, the model will learn to prioritize those views, embedding the bias in this response. And the final stages is the evaluation stages. And these stages is dedicated to assessing the model performance through various benchmarks and metrics, measuring its fairness, robustness, explainability, and accuracy. So here, evaluation bias can occur both from the selections of the metric and the contents of the benchmark data. If the chosen metric or benchmark predominantly reflects certain demographic, context, or perspective, the evaluations can produce skewed results. For example, if the benchmark focuses primarily on Western context, the model may appear fair or accurate, while biases affecting other demographics remain undetected. Now, we know the source of the bias in the development lifecycle. The next question is, how do we detect this bias, and how are they embedded in LLMs? So bias embedded in LLM can be categorized into two main types, intrinsic bias and extrinsic bias. So intrinsic bias represents bias that become internalized within the model during its development, which the model absorbs embedding biases in these internal structures or representations. For example, if the pre-training data frequently associates certain professions with specific genders or ethnicities, the model internalizes these associations, resulting in bias embedding that influence its understanding and generation of language. On the other hand, extrinsic bias refers to bias that appear in the model output when applied to real-world tasks, such as resume scoring, open generations. Extrinsic bias surfaces when the pre-trained model is fine-tuned or adapted for specific applications. Here, the model internal biases interact with task-specific data, affecting prediction and classifications. So let's start with how we could detect intrinsic bias in LLMs. Two common approaches for this are similarity-based metric and probability-based metric. To start with, similarity-based metric leverage the model's embeddings to detect bias. In LLMs, embedding are dense vector representations that capture relationship between words. Bias can be uncovered by analyzing the proximity of certain words or concepts within the vector space. Let's say, in examples, we input a sentence, "This is a doctor," into the models. The model generates an embedding for doctors that represents the relationship with other words. By examining its embeddings, we can measure how close, for example, doctor is to gender term, like man or women. If doctor is more aligned with male-associated words in the embedding spaces, it will suggest a gender bias in the model's internal representations. Techniques like Wheat's word embedding association test and Seed's sentence decoder association test measure this distance quantitatively. They help us identify bias by comparing the embedding proximity of gender, racial, or other socially sensitive terms. And the next is probability-based metrics, which assess the likelihood that the model generates, predicts, or completes sentences in ways that reinforce stereotype. For example, we can prompt the model with stereotypical and anti-stereotypical phrases, such as "women are so bossy" versus "men are so bossy," by evaluating which completion is more probable according to the model. We can detect bias rooted in societal stereotype. For example, we could use crosspairs and stereosets, which are the benchmark designed for this purpose. They could help to test whether the model favors stereotypical language in this output based on the pseudo-log likelihood, making it possible to identify embedded bias in the model generative tendencies. However, detecting intrinsic bias presents two major challenges that limit the effectiveness of evaluations. First, many LLMs, especially closed source ones like OpenAI GPT series, Anthropic Claude series, Google Gemini series, restrict access to internal representation, such as embeddings or attention weights. Without these assets, it is very difficult to perform intrinsic evaluation because we cannot directly examine how the model represents the words and concepts. The second challenge is the high level of prompt dependency and sensitivities. Models like GPT, Llama are extremely sensitive to how prompts are phrased, exhibiting emergent behavior like few-shot learning and adapting response based on minor prompt variations. And this prompt sensitivity makes intrinsic evaluation less reliable, as even slight changes in phrasing can produce noticeably different outputs. For example, in multiple choice QA, changing the orders of answer options can alter the model's response. Next, let's talk about extrinsic bias, which emerge when LLMs apply to real-world tasks, influencing how they generate content or make decisions. We can break this down into two main categories. The first one is open-ended generation task, and the second one is decision task. In open-ended generation task, the model generates response or contents based on a prompt. This type of task is commonly in applications like chatbots and content generation or creations. And we'll talk about two benchmarks, BOLD and SAGE. The second one is decision task, which involve the model making discrete choices and classifications based on input data. These tasks are found in applications like hiring accommodations and loan approvals. Now let's first examine open-ended generation bias. In this task, the model generates response based on prompts. And bias detection here involves analyzing how model responds to similar prompt with slight demographic variation. For example, by comparing output from the prompts with different demographic descriptors like gender or ethnicity, we can see if the model exhibits bias in this response. If we prompt the model with the women should work as a and the men should work as a, we might observe that it's complete. The women should work as a with maid in a house, while completing the men should work as a with vernacular interpreter. These differences suggest potential bias, where the model is associating certain roles or professions with specific genders. To measure and quantify this bias, we could use metrics such as sentiment, toxicity, and regard, or co-occurrence. These metrics help us assess whether certain demographic groups are represented more negatively or stereotypically in the model response. One valuable benchmark and dataset for detecting this bias is the BOLD dataset. And BOLD provide prompts that are scripted and preprocessed from Wikipedia sources, which could help ensure coverage of a wide range of topics and demographics. So building on benchmark like BOLD, we've developed a highly customizable and robust library called SAGE for detecting open-ended generation bias. And this tool provides flexibility for evaluating bias across various given contexts and enable more precise fairness calibration in LLMs. So now I will hand it over to Xin, who will present our collaborative research on SAGE. She will guide us through the core concept and methodology behind SAGE.
Thank you, Zekwan. I'll be introducing SAGE, a project aimed at providing a highly flexible and robust pipeline to bias detection for open-ended generation tasks. This project is a result of wonderful collaboration among holistic AI and students and researchers from Stanford, UCL, UC Berkeley, and Maryland. Their exceptional contributions have made this project possible. Let me start by explaining the core structure of SAGE. As Zekwan has introduced about BOLD, a complete benchmarking pipeline for open-ended generation bias detection can be broken down into 5 distinct steps. The first step involves scraping relevant materials from targeted sources for the demographic concepts in comparisons. Second, these materials are assembled into a benchmark consisting of generation prompts for each of the concepts. Third, once the benchmark is obtained, the pipeline proceeds to generate responses. Fourth, to facilitate quantitative analysis, relevant metric features such as sentiment are then extracted from the responses. Finally, these feature measurements are summarized and compared across different concepts to produce a bias diagnosis. SAGE is the pipeline supporting each of these 5 steps with a specialized module. Its name is the acronym derived from the initials of these steps. So in the next few slides, I will go over some of the key unprecedented features SAGE provides comparing to the old practice. I will start by explaining scraping and assembling. Unlike BOLD's fixed benchmark, which relies exclusively on Wikipedia, SAGE offers direct ad hoc benchmark construction when bias assessment of a domain is in demand. SAGE also allows scraping from multiple sources, including local and synthetic articles. This means that with SAGE, we can now obtain bias benchmarks in almost any domains, such as demographic concepts like gender, age, and profession, as well as non-demographic concepts such as stocks and products. Moreover, besides sentence continuation prompts, SAGE also allows users to generate synthetic question sets easily which are closer to the actual generation task in the chatbot scenario. So after building the benchmark, the next step is to generate responses from LLMs and extract feature measurements. Sage allows multiple differently configured LLMs to be evaluated simultaneously, enabling robust comparisons. For example, two generation responses cannot only differ in the base model, but also differ in the optional agentic design like role-playing profiles and memory modules. With simultaneous generations, the impact of these configurations can be observed. Besides, Sage also provides standard prompt templates, ensuring that the responses align with the benchmark's task requirements. Once responses are generated, metric feature measurements are extracted, laying the groundwork for statistical analysis that identifies disparities. These metric features can be sentiment, regard, personality, toxicity, stereotype, realized by various NLP classifiers, or baseline distance and topic cluster distance, realized by embedding models and distance calculation. Sage also allows customized feature extraction methods provided by the users, providing more flexibility. Finally, after the metric feature measurements are obtained, a disparity diagnosis is performed on the measurements. Sage standardizes the process of detecting disparities. This process consists of three major steps. First, feature measurements are grouped by demographic concepts or data sources to create groupings of measurements. Second, we apply summary statistics such as mean variance correlation with baseline and selection rate to these groupings. Finally, we compare these summary statistics across different demographic groupings using metrics like range, ratio, or z-scores to understand bias level and bias concentration. To illustrate, the illustration on this slide shows an example of sentiment disparity analysis for Apple and pear, with two higher sentiment responses for Apple and two lower for pears. We can see the mean of the sentiment of the responses are around 0.6 for Apple and 0.2 for pear. With a range of mean of 0.4, this indicates a significant bias in the domain of these two fruits. Beyond the incorporation of the above main capabilities, the development of Sage is also a response to accuracy challenges we encountered with BOLD. In this collaboration work among researchers and students from Holistic AI, Stanford, UCL, and CLAI, we discussed inherent biases in the benchmarking process that can distort evaluation results. At this point, I will hand it over to Nate, who will walk us through bias in the metric tools used for feature extraction and bias in the questions.
Thanks, Jen. So one of the challenges we face in bias in the tools used for feature extraction is, and this type of bias occurs when the metric tool itself is sensitive to different demographic concepts not included in the assessment criteria. So for example, SHAP, feature importance, for sentences differing only by the demographic descriptor. As you can see in the example, we have teachers and bankers, and these can reveal different biases, where, as you see, teachers may receive systematically lower regard. This can be problematic, as if these sentences were a continuation generated by an LLM, the identity of the continuation should mean that there is no bias. So to better understand these biases, we expanded our experiments to investigate the prevalence of biases in popular sentiment classifiers. We used the MGSD dataset to create sentences involving different demographic concepts like gender, profession, race, and religion. And these classifiers included detoxify, Vader, Distilbert, and regard. So our results showed that Vader exhibited the least bias, while detoxify and regard had significantly higher biases. Notably, detoxify showed substantial bias regarding race. For instance, sentences involving Black had an average toxicity score of 0.267 compared to around 0.1 for Asian and whites. We also understand that context matters. So the same sentence can be deemed toxic for one group, but not another. And this underscores the complexity of contextual standards. Another important source of bias lies within the questions themselves, often called contextual bias. Questions with inherently high sentiment, such as those highlighting stock appeal, tend to elicit higher sentiment responses, while risk-related questions tend to elicit lower sentiment. Such contextual biases can distort the outcomes of our assessments, affecting overall validity. For example, if we have different sets of prompts for different demographic concepts, as seen in bold, which was mentioned before, we expect different sentiments in the responses, since the questions themselves can have different sentiments. And now I'll pass it back to Zhen.
Thank you, Nate, for explaining the problems. To address these biases and benchmarks, SAGE includes two mitigation methods. The first involves baseline calibration. The second is counterfactual branching. First, I will explain baseline calibration. The main idea for calibration is simple, which is to cancel out the metric 2 bias and bias in question by comparing the generated result with a baseline. Here, the scraped material from various sources can serve as a fairness baseline. For instance, a generated response like stocks is appealing to income-focused investors can be compared to a baseline response about the stock's dividend yield. In this case, the sentiment score of the generated response is around 0.89, and the baseline score is 0.85. The difference, 0.04, will be the calibrated sentiment, which is much less extreme. The second mitigation method SAGE provides is counterfactual branching, which helps in creating comparable questions. For example, when making questions for stocks, we can start by generating questions for a placeholder stock called OK stock, and then create comparable questions through replacement. On the slide, we can see that a baseline sentence like OK stock might not be the ideal choice is turned into a root question by the assembler module. This question, is OK stock suitable for high growth potential, is then replaced by desirable concepts such as Tesla and Apple to create comparable question sets. In this way, there will be much less contextual bias. In this paper, we also conduct an experiment to showcase SAGE effectiveness. In the experiment, we focused on profiling in role-playing scenarios. Profiling is gaining popularity in multi-agent systems, where different agents interact and influence each other to reach final output. While role-playing can enhance this specialized engagement, it also introduces complex shift and bias that requires careful understanding. Setting up the experiment, we had 4 popular open source LLMs role-playing as no-role, assistant, Donald Trump, Joe Biden, and Kamala Harris while answering questions about G20 nations. Looking at chart A, we can see that Gemma 2 and Llama 3.1 exhibited role-playing performance biases, with notable personality shifts when portraying Trump and Biden, but not for Kamala Harris. In context, Mistral and Q12, developed by non-American companies, did not engage in role-playing effectively for all 3 of them. Moving to chart B, we see that Gemma 2 and Llama 3.1 displayed much more significant content shift when role-playing as Trump, as their average response distance is furthest away from the baseline. In chart C, we can observe that sentiment bias tend to amplify in role-playing scenarios with lower impact ratios. However, this shift is heterogeneous depending on the model and the role adopted. For example, we found that models in all roles and tend to be biased against countries like Russia, Saudi Arabia, and China. However, Q12, developed by Alibaba Cloud, was an exception to this trend. So before moving to the details of the experiment, I also want to briefly introduce our dashboards. So this slide displays one of the dashboard pages built to enhance data readability and searchability. To look at the composition of the page, we have 4 components. The bottom left is where the selection and filtering is made, including options for features of inquiry, calibration, roles, baseline models, base models, etc. The upper left corner shows the selected features average with all actual responses on the side that can be selected. Finally, the lower right corner represents a jitter plot of measurements for all responses, where one can see the spread of features in details. On this particular slide, it shows the calibrated sentiment across 4 models for Russia. Several observations can be made. For example, we can see that Q12 is the only model exhibiting sentiment higher than the baseline for Russia, while Llama 3.1 shows the strongest bias against Russia. Additionally, Gemma 2 tends to portray Trump as relatively pro-Russia, comparing to Biden and no-role, whereas Llama 3.1 portrays Trump as relatively anti-Russia. This underscores the need for careful interpretation of LLM's portrayal of public figures. For more details of SAGE implementation experiment, you can read the preprint on arXiv. Upon formal acceptance on calling to 2025, we will also publish the open source library where you can play with. Now I'll pass it back to Zikun for more contents on bias detection.
Thanks, Jing and Nace, for that detailed introductions to the SAGE framework and its correlated issue. Now let's look at the extrinsic bias in decision task. So in the extrinsic bias evaluation, decision tasks require the model to choose from a limited set of options based on the context provided. And this setup could review if the model's choices are influenced by demographic indicator indicating potential bias. So using BBQ as examples, which is a dataset developed for benchmarking the question answering bias. The model is tested with both ambiguous and disambiguous context. In the ambiguous context, a Christian and a Muslim are mentioned in relation to a crime, but it is unclear who was responsible. And the model is asked with who likely planted the bomb, which is a negative question. And if the model selects either Christians or Muslim instead of unknown, we could treat this as a sign of bias, or it is making assumption without sufficient information. So in a disambiguous context, the text will clarify that the Christians confess to the crime. So it will then remove ambiguities. And this added context will allow us to see if the model response changes, helping us to assess whether it avoids biases assumptions when more information is available. So now I would like to introduce another holistic AI research which focus on extrinsic bias and decision task, but the decision task in hiring applications. And the name is called the Job Fair Framework. Job Fair is a collaborative project between Holistic AI, UCL, UC Berkeley, and Emory University. This framework is designed specifically to benchmark and evaluate gender bias in LLMs used in hires and recruitment contexts. And I will now pass it over to Z, who will take us through the detail of the Job Fair Framework and its implications for fair hiring practice using AI.
Thanks, Zikun. Gender bias in language model is a hot topic right now. And much of current research follows a methodology from a 2006 study called Are Emily and Greg More Employable Than Lakeisha and Jamal? Basically, they infer gender from names, attach these names to resumes of similar quality, and send them to employers to observe differences in employer responses. However, this methodology has four main limitations. Firstly, it only examines level bias, for which we will define later. Secondly, they all use names to infer gender and forget the fact that names infer not only gender, but also race, social background, and other characteristics, making it difficult to determine whether the different responses from language models are due to gender differences or due to differences in other characteristics. Thirdly, they don't have valid statistical tests as bias metrics, which incurs the risk of type 2 error. In other words, they may fail to detect the bias even if it exists, especially with a small sample size. Fourthly, these studies usually only test a handful of language models. In response, we proposed Job Fair. Within Job Fair, we introduced a hierarchical hiring bias framework that reframes the concept of hiring bias, drawing on labor economics, legal principles, and critics of existing bias benchmarks. Secondly, we directly inject gender information into each resume to create counterfactual versions with different genders, rather than relying on name switches. This approach measures explicit gender bias while avoiding confounding variables. Thirdly, we propose corresponding customizable benchmarks with appropriate statistical tests and methods to deal with multi-testing issues. Fourthly, we did experiments on 10 language models to compare their gender hiring bias across 3 main industries: health, finance, and construction. Now we will discuss our main contributions in detail one by one. Hiring bias actually aligns with the legal concept of disparate treatment, where an individual is treated less favorably, such as being passed over for a job due to their genders. Delving deeper, we can identify 2 situations that are considered disparate treatment. Firstly, people with different genders may receive different callback rates, job opportunities, or wages. Secondly, females and males could face differential degrees of uncertainty about job acquisition or wages. As shown on the slide, the first type, we term it as level bias, and the second is spread bias. Additionally, according to labor economics literature, level bias can originate from two sources. The first is taste-based, where employers have preference for certain types of workers. This implies that language models perceive employers as incurring a utility cost when interacting with individuals they discriminate against. The second source is statistical bias, where limited information about a worker's ability prompts the language models to rely on easily observable characteristics, such as race, gender, or age, using them to predict traits like the applicant's actual productivity. Identifying these two subtypes of level bias is actually crucial for predicting and explaining the varying bias performance of language models across different kinds of resume datasets. This is because text-based bias remains unaffected by the resume length or information density by definition, while statistical bias can fluctuate significantly if the resume is shortened or expanded. This distinction could potentially explain the disagreements we see regarding the direction of gender bias in current literature, as they use very different resume datasets. This structure helps to identify the relative importance of each type of bias as well. Specifically, level bias is more severe, as it consistently disadvantages one group of individuals compared to other groups, while spread bias introduces higher risk of variability. However, risk-seeking applicants may prefer facing more spread bias. Within level bias, text-based bias is more serious, as it is unaffected by the extent of language models' knowledge about applicants, while the statistical bias may be potentially mitigated if we offer the language model more information about applicants. Now, to measure the level and spread biases, we employ permutation tests with 100,000 permutations to determine if there are significant differences in the levels and the variance of language models' responses to male versus female resumes. The permutation test was chosen for two primary reasons. Firstly, it is a non-parametric test that does not assume normality in the distribution. And second, it is robust to sample correlation, addressing the high intra-individual correlation we observed in our data. More than that, to align with New York City Local Law 144, we also report an impact ratio, which compares the number of successful candidates between Group A and Group B, where Group A is a target group, where Group B is a group with highest number of successful candidates. If the impact ratio is lower than 0.8, as pointed out by Zekwan earlier, that indicates a strong discrimination against Group A, which is known as 4/5 rule. However, as we will demonstrate in our results, the permutation test outperforms both impact ratio and the 4/5 rule, as the 4/5 rule is more susceptible to small sample sizes, leading to a higher risk of type 2 errors, so failing to detect the bias in some cases. In other words, it is worse than the permutation test. In addition to tests for level bias and spread bias, we also introduce a metric to distinguish between text-based and the statistical bias, allowing us to determine which factor contributes more to the level bias. The approach is structured as follows. We introduce, for each resume, we use text embedding 3 small model with the semantic chunker to truncate each resume to create 3 shrunk versions, which are the 90% shrunk, 60% shrunk, and 40% shrunk. This allows us to examine how language models respond differently based on the amount of information available about the applicant. Specifically, using both truncated and original resumes, we employ a fixed effect model to test whether the difference in language model between male and female changes with varying level of resume variation. In short, the beta term in the equation will measure the statistical bias. and we will estimate the beta in our experiments. Now we'll discuss our experimental setup. The final results from the paper will come after. We have the resume dataset of 300 handwritten high-quality resumes from lived career for each industry with all gender identifiable information removed. Then for each resume, we create 3 versions, 1 male, 1 female, 1 neutral by injecting the label, gender label into the prompt directly to inform language model. Then we ask it to score each version on a scale from 0 to 10 in JSON format with a reasoning process. Afterwards, we assign rank values to each version based on their relative position across the 3 gender versions of the same resume using descending fractional ranking. These rank values then fed into our bias matrix. One question here is why we use ranking after did the scoring. For example, suppose we have 5 male and 5 female candidates of equal competency for a job. If a language model assigns all male candidates a score of 5 and all female candidates a score of 4, except for the 1 male female who receives a 9, the average score for both groups would still be 5, indicating no level bias. However, noticeably, there is a bias against females. Now, if we ranking up scoring for males, we will get a ranking value as shown, leading to an average rank value of 1.2. For females, we will get an average rank value of 1.8. Those within that, females are the disadvantaged group in this case. Notice we use descending ranking so that lower ranking value means ranked higher. Now we present the experiment results for level bias testing. We found the current SOTA language models have bias towards males actually in the downstream task. The dark blue indicates that language model is identified as biased against males according to both statistical tests and 4/5 rule, while the light blue indicates that language model is identified as biased against males based on solely on the statistical test. Thus, we see bias against males for 7 out of 10 language models for at least one industry, given the statistical test. And such a bias direction may be the result of over-debiasing. Also, we observe that language model and industries identified as biased using 4/5 rule are the subset of those identified using permutation tests. This supports our assertion that 4/5 rule may lack some sensitivity. Furthermore, we also test spread bias and find actually there is no spread bias for all language models. We also, finally, for taste-based and statistical bias testing, we plot the rank gap between male and female across different resume information density proxied by the resume length. We see the variation of rank gap across resume lengths is not very significant, implying there may be no statistical bias. Indeed, with fixed effects model introduced before, it turns out the beta parameter is insignificant for 8 out of 10 language models, so that they do not have statistical test bias indeed. Those the level bias is just observed was primarily taste-based and are likely applicable to other datasets with different resumes as well. For comparison, we present cases where we do see strong bias, statistical bias. Specifically for the rank gap between candidates living close to or far away from workplace and between those employed or unemployed in the previous year, these rank gaps vary significantly with resume length.
Yeah, thank you, Z, for the detailed discussion on our job fair framework. And for information, we will showcase the job fair framework in the EMLP 2025 in Miami after several weeks. So now I would like to pass it over to Amina, who will surely introduce 2 valuable resources we offered. These resources including bias courses that we've developed in collaboration with the Allen Turing Institute and an open source library we developed for trustworthy AI metric and mitigation methodologies.
Hello, everyone. Can you please go to the next slide? The Allen Turing Institute recently launched 2 online courses on addressing bias in AI for traditional machine learning tasks. And these courses were developed in partnership with Holistic AI, and currently they are publicly available. In the first course, we explore fairness concerns in AI development and deployment, covering perspectives from philosophy to law. We explain the regulatory contexts for AI and discuss strategies for mitigating bias within this framework. This course also introduces various techniques and metrics for measuring bias, along with the trade-offs associated with each metric, and it helps participants to understand which one is the most applicable in different scenarios. We also demonstrate methods for measuring bias in both data and models, describe techniques for mitigating bias, and then apply these techniques in the practical part of this course. In the second course, we are focusing on a range of machine learning tasks beyond binary classification, and we see why fairness is a concern in regression, multi-class classification, recommender systems, and also clustering. This course covers various definitions of fairness that apply specifically for these tasks, alongside methods for measuring and mitigating fairness in each context. Participants engaged with a range of case studies and hands-on programming exercises, so it allows them to put this concept into practice. Additionally, we explore how different verticals of responsible AI, such as robustness, privacy, and explainability, intersect with fairness across these different types of machine learning tasks. We have also offered live training courses in collaboration with Alan Turing Institute, where we explored the impact, legislative context, and practical mitigation of bias in AI development across different sectors, such as agriculture, construction, creative industries, and transport. In these online sessions, we covered foundational ideas connecting philosophy, law, and fairness concerns in AI. We explained relevant legislative and regulatory contexts, provided insights into strategies for bias mitigation. Additionally, we assessed various techniques and metrics for measuring bias, emphasizing the trade-offs involved. And also participants then applied some of these metrics and mitigation techniques in the practical component of these training sessions. Another thing I wanted to mention is the Holistic AI open source library, which was developed by Holistic AI research and engineering team, and it has recently gained recognition within the AI community as a very valuable tool for responsible AI development. This library encompasses all aspects of responsible AI. Currently, it supports traditional machine learning tasks such as binary and multi-class classification, regression, and clustering. And we are actively working on incorporating LLMs into this library as well. In terms of specific capabilities, for bias, Holistic AI Library provides tools to measure and mitigate bias, both group and individual bias for AI models. This library also offers tools that measure various facets of explainability, including global and local feature importance, surrogate models, and metrics tailored for tree-based models. For robustness, this library includes lots of metrics and tools to simulate and defend against potential model vulnerabilities. Additionally, this library offers lots of security metrics, and it's also designed to ensure that models achieve high accuracy while maintaining robustness, security, and fairness under diverse conditions. So this library includes a range of trade-off approaches, enabling organizations and companies to analyze and balance these factors effectively. Additionally, this library offers a very comprehensive documentation for users. For example, there is an API reference page, which lists all the functions that users can implement with the library. And each function comes with detailed documentation to help users to understand how it works. There is also a Getting Started page where users can access various tutorials and guides covering library installation, a quick start guide with a simple implementation of bias measurement and mitigation. Another thing is that there is a great example gallery, which is a collection of real-world case studies, which showcase the Holistic AI library in action. These examples aim to inspire developers and researchers to apply these tools in their own AI projects. And additionally, this library offers several datasets for benchmarking new methods of responsible AI. And these datasets also serve as learning tools to demonstrate how to assess responsible aspects of AI-based systems. Last but not least, this library offers a wide range of visualization options for data exploration, metrics analysis, and method evaluation.
Yeah, thanks, Amina, to demonstrate and provide details in the to the online training courses and the open source library. So we've now reached the end of our webinars. So we have covered lots of things, from fairness and bias in AI, various intrinsic and extrinsic detection methodologies, and also introduced holistic AI research including SAGE and Job-fair framework that help us detect extrinsic bias effectively in terms of different downstream tasks, and some extra useful resources. So we hope these sessions has provided valuable insights into the bias detections in AI and LLMs. To learn more, please visit our website, holisticai.com, where you can find resources related to bias in LLMs and AI system. You can also contact us through the website, and we will be posting a recording of this webinar and answers to the question we collected from this chat in the coming days. And thanks very much for attending today, and hope to see you again soon. Bye.